Okay, we're back, and this is something about rotational motion. In particular, this is kind of the setup, where I just would like to introduce some analogs to linear motion. Basically, what you typically do in a first-year physics class is usually not rotations. Most classes will probably hit something like circular motion, where you talk about like a ball at the end of a string, a pendulum, the Earth going around the sun, different kind of orbits and satellites and things like that. Circular motion refers to point masses going on a circular path, and that's where you deal with the concept of centripetal force, mv squared over r. Rotational motion is different because now we're talking about spinning objects, where all points of a real object are spinning around some common point, which we refer to as the axis of rotation. That could be like the rotation of the Earth, tops and gyroscopes, dreidels, spinning a basketball on your finger, something like the hands of clocks going around, figure skaters who spin wheels are kind of the poster child for this, and so on. So many students find rotational motion to be perhaps the toughest unit within mechanics, mainly because you don't typically have a lot of previous experience with this. So what the purpose of this video is for is to take the common features of linear motion that you already know and are more comfortable with, and show how basically everything we do with linear motion will be done in rotational motion, just with new symbols, new units, but the analogy is going to be there. The same type of thinking, the same types of concepts will be present. So, to get started, we know that we have the three main quantities that we need to describe motion in the first place would be linear displacement, velocity, and acceleration. So displacement, of course, is how far you travel and what direction you're traveling. Okay, it's related to distance and things like that. And we're going to have a similar thing for rotations. So if we imagine something like a wheel, and you look at the spoke, a spoke on a bicycle wheel, and if you rotate the thing, say so that you rotate it 1/4 of a turn, there's an angle that spoke has rotated through. We're going to call that theta, and the name of this is going to be called the angular displacement. So rather than how many meters you travel, this is going to be how many radians have you actually rotated through. And make some more room here. Now for velocity, which we know is the rate of change of your displacement. Okay, in physics C, for example, write that as a derivative. And this will have units of meters per second. We also have, for that spinning bike wheel, how fast do you rotate it through a particular angle? And that'll be called the angular velocity, whose symbol is omega. Okay, a curvy W, Greek letter that looks like a W. And that'll be defined as the rate of change of your angular displacement, and we'll have units of radians per second. Of course, it doesn't stop there. We have the rate of change of velocity in linear motion, okay, just acceleration. We have units of meters per second squared. And as you probably have guessed, we have an analog in rotational motion. If we speed up or slow down the spin of an object, we'll talk about an angular acceleration, whose symbol is alpha. And that's defined as the rate of change of your angular velocity. And let's have units of radians per second squared. Okay, now it turns out there's a nice connection between these linear and rotational quantities. And we can still use a analogous to that spinning bike wheel, something that you talk about in trig, I think. That's the notion of arc length. So if you have, for example, something starting at some point, at some radius, and let's say you start to move on a circular path around that center point, you move through some angle, theta. The actual distance in meters that you travel along that arc is the arc length. And as long as you're measuring your angle in radians, there's a connection there between the linear distance and the angular distance, or angular displacement, S equals r theta. Now, if you were to take this, and let's say you look at the rate at which you move along that arc. Okay, well that's the velocity. And if you do a time derivative on one side, you have to do a time derivative on the other side. Now if the radius is a constant, notice that you have r d theta dt, which is radius times your angular velocity. So it turns out that you have a similar looking relationship between linear speed and angular speed. And again, you could do a time derivative of that velocity if things are changing. And that's equivalent to the radius times the angular acceleration. Okay, so this set of equations is often useful in problems if we have to go back and forth between linear motion and rotational motion. Okay, now something neat kind of happens. If you have constant acceleration, we know, for example, in linear motion, we have a set of equations that hopefully look very familiar to you. You do a lot of this in a first-year physics class. And then we have, at Evanston, we call this the forgotten equations. It's just a combination of the first two. It's often very useful. Oops. Well, it turns out that you have exactly the same types of relationships in rotational motion. For example, if you imagine taking this velocity equation for linear motion, if you divide all three terms by radius, well, velocity divided by radius is angular velocity. And so if you have a constant angular acceleration, you have an angular velocity equation, you have an angular displacement equation, be 1/2 alpha t squared. That's your initial angular velocity and your initial angular position. And you have even a forgotten equation. That looks something like that. So you run into very similar types of problems in rotations that we encounter in linear motion. If you have a constant angular acceleration in so many seconds, what's your angular speed? What angle did you move through? Things like that. Okay, so these are just the three basic quantities again, and we have constant acceleration equations. In rotations, we take concepts like force, which is measured in newtons, and we have an angular equivalent of that. Okay. Well, what do forces do? They cause acceleration. They cause an object's motion to change. In rotations, force by itself is not enough. We have to define something called torque, which in my classes we write as force times the radius times sine of some angle. Well, what that means is if you have, say, a bike wheel, any kind of wheel, Okay, it has a radius. And you can imagine if we apply a force to this thing, the only way to make it spin isn't if we push on it sideways, where it's parallel to a spoke, or parallel to a radius line. That's not going to make it spin. Instead, what we have to do is you have to grab onto the rim of a wheel, let's say, and maybe pull down on it or push up on it. You need a tangential piece. That's what that angle refers to. That's the angle between that radius line and the direction of your applied force. Okay, so you need some distance from the axle of the wheel to where you apply the force, and you need an angle between the radius and that force you apply. And that's called torque. It has units of newtons times meters. And of course in class we get into much more detail about this. I just wanted to define it here in this for the video. We're going to have a change in mass. Okay, so for linear motion, all we care about is like how many kilograms it is. We know F equals ma. The trouble is mass by itself is not all that matters when it takes into account rotating the object. Instead, we're going to have something called the moment of inertia. That's going to replace mass where we're used to seeing mass. The symbol's going to be a capital I, and it's going to have funny units of kilograms times meters squared. I've got some videos on how to find these moments of inertia for sticks and for a disk, and we'll encounter some other shapes and other types of objects in class. Now, combinations of these, we know that when you have a net force, that causes acceleration of an object. Well, we can play this game now with equations of substituting in the analogs. So instead of force, for rotations, if we have a net torque, which is a vector quantity, that's going to be equal to your inertia times angular acceleration. Okay, so there'll be a Newton's second law of rotations, basically. For things like, say, momentum, linear momentum, there's going to be a rotational analog. Angular momentum, the symbol tends to be a capital L. Inertia replaces mass, and omega, your angular velocity, replaces linear velocity. Things like kinetic energy. 1/2 mv squared is often referred to as your translational kinetic energy, linear kinetic energy, if you want to call it that. But when something just spins in place, it takes energy to do that. We call that rotational kinetic energy. I, your moment of inertia, replaces mass, and omega squared is going to replace v squared, and so on. This will still be measured in joules. Angular momentum is going to have units of joule seconds, it turns out. And torque, like we said, is going to be Newton meters. Okay, so this is just our laundry list. This is just a set of equations and some new symbols, new units that we're going to be using time and time again when it comes to rotational motion. And keep in mind, before you start getting worried or too freaked out about all this, it's so beneficial that these relationships that we're used to are going to have analogs pretty much every single time, just by making these simple substitutions of quantities. So we'll have a lot of the same ideas. Energy is going to be conserved. We're still going to have conservation of angular momentum, just like linear momentum. And we'll do all this stuff in class in great detail. But for now, just keep in mind, we're going to try to make this as familiar as we can, keep it as simple as we can, and we'll build from here. So I hope this introduction helps, and until next time, see you later.